Next, we would like to have Professor Li Danjiang from Tsinghua University to share with us his presentation in light and NOS. Good afternoon, ladies and gentlemen. My name is Li Dan from Tsinghua University. I want to give introduction of light and NOS. What are the main research we have been doing? Because I only have 20 minutes, so I won't be too specific. I will just tell you what we have been doing. I only have time for the brief introduction regarding technical details. What is the advantage of our DPDK community? We are very aware of it already. We can deliver 80 CPU cycles. Because we have always been in such an industry. What I care the most is how to take fully advantage of the DPDK performance gain to provide better services to the applications. For the network technology, after developing for decades, only in the recent few years with NSD and FB are we feeling more excitement. But for the past 10 years, network technology doesn't enjoy that much development. With DPDK, we were thinking, is it possible for us to separately put in the user space level for network? Many of you may have think of the same issue as well. So for the codes and the stacks, not many of us are doing maintenance, but DPDK provides great opportunities. To the protocol stack, we have done all sorts of automations. We also have a professor from South Korea give us an introduction to MTCP as well. MTCP is based on DPDK. It is also realizing the network operation as a threat application. We also have 6WIND. 6WIND as a commercial provider. I personally don't know too much of the technical details. Exactly what we want. We would like to develop a DPDK-based network stack. Using this stack, we will be able to provide functionality of network operating system. For this network stack, this will be the overall architecture. There are multiple applications. This is operating system. DPDK is the I/O drive, and then we have the net card. We want to develop an application layer stack. We call it net. We would like to have it provided by net. For the non-network API, it will still be done by the operating system. Regarding the data flow, when we have the NIC through DPDK, it will come to the application layer stack, etc. For the API's utilization, besides the application would use NET, as well as non-network API. NET protocol stack, if it can use DPDK API, it will choose DPDK API as preference, including the memory management and other network and I/O. To do this, we are doing our best to reduce the system call overhead, but unavoidably, it will use the dynamic link library and the signal processing from the kernel. For light architecture internally, it has 3 different modules. We have net light parser. It has a lot of code, but it's very simple. Basically, we can have all of the code. The second module is light daemon. Light daemon is more catered to manage the queues. It is one interface of light parser. The third, we have light API. For all of the APIs, we will have it to realize that. So for realization of the code, it can also be regarded as reference. What is the purpose of doing this? The purpose is very simple. When the stack is completed, if we want to use it on the application layer, we need to minimize the modification to the application layer. The best we can do is to no need to modify application layer. We will develop many new applications as well and migrate existing application. This will make the follow-up migration more simple. Today is a DPDK community summit, but to the users, they are not willing to increase the cost in migration. The second goal is to minimize the performance effect to the applications. The reason we want to use DPDK is to increase the I/O performance. To increase I/O performance, we can enhance the systematic performance altogether. But DPDK requires a lot of CPU resource. If the DPDK started to affect the application performance, then it will be losing the original targets. So for the two goals we are aiming to achieve, I want to give introduction to our technologies. Let's take a look at the first goal, how to minimize the modification to the applications. Light provides network-related APIs as a lib2 applications. I only would like to talk about the main challenges. The first challenge is because in the kernels, it also has I/O APIs. If we are using Light to provide network-related APIs, there must be a way to mask the network APIs of the kernel. It will be difficult to cut the kernel. A lot of unexpected cost will be there. The second challenge is if you use Net and kernel, Light and kernel are providing different APIs. Then there will be the FD space issue. Anything related to network and the socket, the FD space are provided by Light, but those regarded to reading, it still has to go through kernel. So how the application can differentiate the two FD spaces without modification to the application. Next, I will give introduction to our solutions. Our current outcomes is we just need to add one specific function during defaulting. But we want to delete this function in the end as well. Talking about API mask, we use a lot of redirection of the function address to Light. So through the redirection of the function address, we will be able to provide the API of the application using Light. In this way, you don't have to modify the names of the APIs. You don't have to modify the operating system's kernel either. Regarding the format of the spaces, we can be more accurate. For the FD spaces, firstly, it will cause a confusion if the application has a read or write. Read and write can be socket and can be files. So how can we know whether it is socket or files? Since you don't modify the applications, this is the confusion caused by FD directly. The second confusion is to realize equal. For equaling, it needs to hypervise the events. It can be network socket events and can't be file events. If we use kernel and NAC to provide it separately, then there will be two equal. For two equal to work at the same logistically, it is not manageable.
So finally, how do we deal with this? How do we address it? Firstly, about the first problem. That is about the 2FT space confusion. The current solution is like this. Currently in the Linux system, when allocating the FD, it's from big to small. In the namespace, we search for the available ones, and then in the light, when we allocate the sockets, it goes from small to big because it's 32 bytes, and the space is like more than 4 billion, so we believe for a machine we can make such distinctions. Like for applications such as read and write, if we hijack it with light, then we can judge it by its FD size to see if it processes files or whatever. And then for the equal, we have two solutions, but they have their respective strengths and weaknesses. If we want to listen the network socket events as well as file events, then we can switch to non-congestion mode. That is, there is the external network circulation, and if there's an event, they will return it to us, and then we can determine whether it's read and write for the socket or for the file. But here's the issue. If you are in non-congestion mode, it will have to occupy a lot of CPU, and it's used in the equal, and it is called by application, so that will compromise the performance of the application. But if we want the equal to maintain the congestion mode to save on CPU, then what we may do is that we may take the socket, including the socket of the processes, and provide them in the light. But then we cannot support read and write of the files. Sometimes it's okay because we don't use the equals to listen to the files, but otherwise we may have issues. Therefore, we prefer solution 1. And the second challenge is like this. How do we minimize the protocol station's impact on the performance? There are two aspects of it. As I said, DPDK is based on polling, so the CPU use is 100%. I understand that Intel is making progress and doing a lot of work and making a lot of improvements, but anyway, DPDK is based on polling. That's one of the basic technical features, technical characteristics, so it competes for CPU resources. And secondly, it will take over a lot of the features, so we need to redesign the inter-process communication, which may have impact on the performance. So if we want to minimize the interference with the application's performance, we need to address these two issues. So okay, first about the contention for CPU. Here's our solution. I mentioned 3 modules. Parser and daemon run on the same core, and app and light API run on other cores, so that parser and daemon, let's say we have 8 cores, and 3 of the cores will do these. And light API and other things will run on another core, so that they will not be affected by polling. This means that when reading and writing the data, the net card will first get to the net core and then the application core. We believe there may be some conflict if we fully localize the data, but I believe this solution is a better arrangement. And secondly, about the inter-process communication about the light protocol station as well as the inter-process communication. The basic mechanism now is based on DPDK RTE ring. It's about sharing the memory and it's lockless queue based. The issue we need to address is that there's a lot of congestion code for the processes. As you can see, ePO, receive, send, accept, connect. They can go into the congestion mode. So if we pull the kernel, then if there is no data arriving, then it will be suspended and save a lot of CPU. But now, for the light protocol, here is how it is addressed. There are two possibilities if we want to address the situation. Option 1. In light daemon, there is a queue for reading and writing, so if light API is used to read and write the data, if there's no event, then I will let the application go into hibernation. If any data arrives later, we will wake up the application. By doing this, we can achieve something like the application core kernel. However, there's one issue with that is we're waking up the daemon. There are two possibilities. One is that the signal may be poor and you may lose signal. And for the worst case scenario, it may be like this. This is the last message arriving, and if you lose it, then it will never be woken up. And another possibility is the sequence, because it's about switching the status between different processes. It has to be called for by the system. So we first wake it up when the data arrives. So the situation is the application signal first arrives, and that's when the application is still active. Then we don't have to take actions, and then the application goes into hibernation, and then in future there will be no signals. No signals will be able to arrive. So the last event or last packet, if there's lost, how do you deal with that? And the second approach is like this. The second method or option is like this. It's not based on the kernel congestion. Rather, it is more like a mixed interlock. It's more like a hybrid spin lock. And for this approach, it can reduce the CPU usage. However, it still increases CPU overhead. These two options have their respective strengths and weaknesses. What we finally choose is this one. Actually, I have a new set of slides. This slideshow is not the latest version. Anyway, I will just talk about it. Finally, how we address it is like this. If you look at these, if you look at this API, they are different. About ePO, it targets any socket in the process and any event in the socket. It listens to any of them, and if there's any of them, it will process it. But the other APIs only look into one socket and only for specific events such as sending, receiving, or writing, or reading. They are different. So when we actually do it, if we use ePO, then there's very little likelihood of losing the packet, almost impossible. I mean, if the process is running, all the sockets and all the events, only if all events and only if there's no event with all sockets in the process when the process is running, so it's almost impossible. So we use EPO because we want to see if there are any events to deal with it later. So the congestion mode is meaningful for it, but for the other API, it's possible that such error may happen. Even though the likelihood is low, but it's possible. So we take this approach, which is like the spin lock. There is the circulation, and then it sleeps for a while for every cycle. I cannot go into greater details for the interest of time. Now, please allow me to wrap up about this light system and how its features are. Compared with other protocol stations, we have three features, three highlights. First of all, we want to achieve network operating system. That is the function we want to achieve. That is, if the protocol station has rather comprehensive features like inter-process communication supports and so on. That's the first thing. And the second characteristic or highlight is that we want to minimize the modification to the applications. Now we have to add one function when we started, but in future we want to achieve zero modification for the applications. And thirdly, this protocol station should not have interference to the performance of the applications. We don't want to compromise the application's performance because of the use of DPDK or anything. That's what I have to say. Thank you. Any questions from the floor? The signal link, the signal volume, well, that was unacceptable because it compromised the performance too much, way too much. About your codes, what's your plan? Is that going to be open and for everybody to download? Do you have any plan like that? Well, now for the monocore version, we have completed it already. Now we are still making the multi-core version. We do have a basket of plans. We are in a university, so we do pursue technologies mostly. Any other questions?